I think let's get started, Ron.
Yeah, sure. So it is my pleasure to introduce Rohan today. He's a PhD student at UC Berkeley, and he works in program synthesis. And his work is, I think, one of the most beautiful intersection I've seen between programming languages and software engineering. I'm looking forward to hearing Rohan's talk. Take it away, Rohan.
Thanks, Rahul. Let me share my screen again. Okay. Just confirming, you can see my screen again.
Yeah, we can see it.
Perfect. All right. Okay. Awesome. So yeah, thank you for the kind introduction again, Rahul, and thank you for inviting me to talk at this seminar. Today, I want to talk about the work I've done in program synthesis, especially targeting data science applications. And time permitting, I also plan to outline some discussion points around the future of research in this particular area, like my personal view and what we're working on next at Berkeley. And I hope that amounts to a nice, interesting round of discussion with you folks. Before I begin, I do want to clarify that I'm not really a formal methods person. I feel this is important to say, given the title of the seminar includes the word verification. I do come from a software engineering background, and this will be evident from the problem statements we pick and the solutions we come up with. But nonetheless, I do hope that you folks will be able to find some interesting nuggets here and there, and I'm excited to know your thoughts on them as well. All right. So data science, I'm sure many of you have come across these attention-grabbing headlines in the last few years, with the underlying message being that data science is now being given a lot of importance, and there is a huge growth in the number of practitioners of data science in the last few years. Tasks in data science mostly fall in these 5 buckets: data collection, cleaning, exploration, building machine learning models, and deploying them. And there are many tools available to aid data scientists in these tasks. And they roughly fall into 2 buckets. One of them being end-to-end platforms and the other being libraries and APIs. Platforms provide automation and graphical interfaces for most common stages of a data science pipeline and provide a high level of convenience when it comes to applying data science in these restricted settings. On the other hand, these libraries and APIs are meant to give the utmost flexibility to the user because they involve programming and therefore they come with a lot of power and expressiveness that is very useful to data scientists. And in this talk, I want to focus on this class of tooling, primarily programming libraries and APIs, because they still remain the weapon of choice for most data scientists, primarily because of their expressivity and powerfulness. And I want to quickly just start off by stating the problem itself, because since these libraries come with all this power and flexibility, they do come with their own sets of problems as well. And then the primary problem is that using these APIs can well be frustrating. And the primary reasons are that these libraries are often very large and complex. Their documentation is dense, and there is a lack of sufficient examples within the documentation. So if you're someone who's new to these libraries, who's just starting out, this presents a very steep learning curve to get started with using these effectively and efficiently. Here's a case in point. There's this library in Python, Pandas. I do think some of you may be familiar with it. And suppose someone is just starting out and they look at the documentation of Pandas, very quickly they would be faced with this rather daunting list of API functions. And the sheer size of the API may be overwhelming. And if you're looking for a particular function, it may take you some time to get to the right one. And even if you do get to the right one, it can be frustrating. The documentation can be overwhelming. There are often not too many examples of a single function, let alone how to compose different functions to achieve a particular task. So how have people been coping with this problem so far? And the remedy essentially is forums such as Stack Overflow. And I'm sure everyone here has used it at some point or the other. And the great thing about Stack Overflow is that more than a question answering forum, it serves as a rich treasure trove of reusable examples. That is, Stack Overflow has a nice collection of code snippets that we can repurpose for use in our own setting, or a data scientist can use in their own setting. So here's a simple model of how developers might search for or reuse code they find on Stack Overflow. They would provide a search query. They would go through the code results, or if you're working in data science, you might you look at visualizations if they're part of the query. And while going through the results, you probably need to understand the code snippets that are provided in the answers to these questions. And if you do find something suitable, you may have to first modify or adapt it before you can use the code snippet in your own workflow. And the problem here is that all of these three steps, searching, comprehension, and adaptation, all of them can be non-trivial in many cases. Searching can be non-trivial because as a recent study on code search by developers found that, writing these natural language queries for code snippets, although they are very frequent, they can be quite difficult to write because sometimes it's just hard to explain what you want to do. And you may have to rephrase your question many times before you get to the right one. Code comprehension, it doesn't need too much justification to say it can be non-trivial, because if the code is large or if it involves many unfamiliar functions, it may be difficult to understand what exactly is going on and to figure out the assumptions that need to hold for the code snippet to work in, say, your setting, if you're trying to repurpose it. And as another study on how developers utilize code from Stack Overflow found, incomprehensible code is one of the main reasons behind less reuse of snippets from forums such as these. And finally, the same study had found that adaptation is a major barrier as well, because the code needs to be modified in majority of the cases before you can use it in your own workflow. There are very few cases where you can simply copy paste and things will just work. So here is an example to drive the point home. Suppose you want to make a plot like this, right, where there is a bar for every distinct value of a variable, and each bar itself contains a distribution of another variable. So this kind of a plot is called a normalized stacked bar chart. And say you want to use a plotting library like matplotlib, so you would go on Stack Overflow and Google and just search for this phrase, find code snippets on how to do this. If you actually search for this, it turns out that on Google, only the 5th result is actually relevant. And it's relevant because it actually contains the plot in the answer, which looks something similar to what we're looking for. But if you look at the code, it's a mouthful. There are many things going on here, and it would take you a while before understanding what exactly is going on and how you need to rename the columns, use different functions, or eliminate certain lines before it can work in your own setting. So this is the opportunity I want to highlight here. Essentially, there is value in creating synthesis-powered productivity tools for data scientists. No-code or low-code solutions where users can easily specify what they want to do. Something that is easier than spending all that time on Google and going through results. Second, the user should be able to obtain personalized solutions, and that to add interactive speed or something within a reasonable time frame, because if it takes too long, the users will just drop it. And finally, the integration of the result should be smooth, something akin to how IDEs are these days when it comes to integrating developer suggestions within the code itself. And it is worth noting how popular programming assistants like Copilot have become recently, but I think there is room to go beyond just code completion or automation of generic tasks. We can go further beyond. So this is a great opportunity to have research in this space.
Rohan, a question. When you say go beyond Copilot, what are you envisioning?
So beyond just like describing a task in natural language and just looking at the complete the text and verifying it ourselves. Maybe we can have a multimodal approach where we can have other specifications like input output examples, or have more like interaction based modalities where we can be more expressive about what we want, and the assistant would pick up on that, and even go beyond tasks that can be described by natural language, because as you'll see in a work that I'll discuss now, when it comes to visualizations, you want to be able to look at many different visualizations to kind of pick what you want, and in those sorts of cases you need to go beyond these sorts of modalities.
Okay, thanks.
Any other questions before I move on to the next part? Awesome. So in the next part of the talk, I'd like to talk about some of my own research in this space. And in particular, I want to outline 3 papers that target synthesis, specifically for data processing and data visualization that were published in the last few years. So let me start with the first one, AutoPandas, was published in 2019, a couple years back. And AutoPandas, as the name suggests, is a synthesis for the Python pandas library. So why did we pick pandas at the time? Well, it was and it still is the most popular library in Python for manipulating and processing data. It is also the most asked about. In fact, 2 to 3% of all Stack Overflow questions are tagged with pandas. The graph on the right shows how that compares against other popular libraries such as TensorFlow, PyTorch, Matplotlib, etc. So because of this gap, we thought pandas was a good place to start. So before I dive into the actual approach we took for synthesis for pandas, I want to give you some insight into the decision-making process behind the approach that we took, especially in the context of past synthesis literature at the time. So just to recap, and I'm sure everyone is familiar, but I'll just recap it for completeness sake. So what is synthesis? Essentially, you have a user who provides a synthesis specification, which is essentially a specification of their intent, what they want to do, and which is passed on to a synthesis engine, and the engine comes up with a program that satisfies the spec. And as Sumit Gulwani and others pointed out in the program synthesis book, there are 3 main dimensions under our control when we are designing such a synthesis solution. The first is in the form of the spec, or the way the user specifies the intent. I'm not sure if there's a question. All right. So the first dimension under our control is the form of the spec, or the way the user specifies the intent. The second is the space of the programs that the engine can output. And the third is finally the algorithm used by the engine to arrive at the answer, or searching through the space. And based on prior work, this is like a grid of choices for each dimension, something that has been adopted by notable prior works in this area. And so if you select a few tiles in each row, you can obtain the crux of notable prior works. For example, if you pick formal specs and program sketches as the modality and the search space, and if you use something like constraint solving and CGIS, that is essentially the program sketching technique invented by Armando Solá-Lezama. Instead of sketches, you start using grammars to define the search space. That is essentially what roughly gives us the family of syntax-guided synthesis problems. Flashfill popularized the use of input-output examples as the specification modality, and they combined DSL, a small search space, so with deduction-based techniques that operated over the data space, or the space of the input-output example itself. It used divide and conquer on that. And more recently, with the effectiveness of deep learning, there are solutions like RobustFill or Seek2Sequel, which rely entirely on models to generate the end-to-end programs, which are still contained in the DSL or grammar. So with this in mind, all these choices from the past literature in mind, how do you go about tackling synthesis for pandas? So first of all, we had to pick a specification modality. So for auto pandas, we picked the input-out example modality, first because it was commonly used in synthesis literature, and it made sense for pandas because most of these Stack Overflow questions, they came with an example which the users used to aid comprehension of the problem itself. With regards to the search space, we found it difficult to try modeling pandas semantics using SAT or SMT. So those that way of expressing the search space was out of the picture. And general text-based models, like what language models are these days, they were not really as popular during the time, and it seemed too far-fetched, so we didn't stick with that. So DSLs and grammars were the next best option. But there are a few catches here. With pandas, the search space is pretty big. There are more than 300 functions within the library just for data frame or like table manipulation tasks. Moreover, the search space is highly dependent on the input. So many pandas function calls often need constant arguments that are derived from values in the table, such as column names or the precise or the minimum or lowest values in the table. So if you want to actually define the search space, that is actually a function of the input. You can't just have it a static for all possible inputs in the library. It is also hard to define the search space precisely because of the number of constraints that need to be satisfied for programs to be valid. Moreover, it's difficult to express these constraints outside of the library. So as an example, the drop function in pandas has this constraint that if the value of the axis argument, it can range from 0 to 1. If it's applied as 0, then labels must be a list of row labels. And if it is 1, the list of column labels, then label should be a list of column labels. So they're mutually dependent. So because of this, DSLs and grammars were not looking like the best choice because we wanted to capture all these additional constraints as well. And we perhaps needed something as close to real code as possible. So we wanted to innovate on this search space side of things. And coming to the algorithm itself, again, we couldn't rely on SAT-SMT based techniques because we weren't able to use that sort of modeling. And now we could rely on the machine learning models available at the time to work with such a dynamic search space as this one. And using a flash fill approach was also difficult because writing these deduction rules for such a large API would prove to be a pretty hard task. And similarly for implementing a pruning strategy when it comes to enumerator synthesis. So this kind of is roughly how we arrived at a solution looking at the domain of pandas. And the solution that we came up with in summary is essentially borrowing the concept of generators from the testing community, if you're familiar with that. And we used enumerative synthesis along with ML bias using neural networks. And the resulting tool that we came up with, we call that neural back generators. So I'll just dive into the specifics, but this is the high level picture of how we ended up tackling this particular problem. Again, yeah, I do want this talk to be informal. So if you do have questions, please just ask in between. Yeah, I think Ravindra raised.
Go for it, Ravindra.
Yeah, I just want to know, how do you capture the IO specifications in this case? You know, the output is a picture, right? Graph. How do users give that graph if they know already? I mean, your specification modality is IO specs, right?
Yeah, so the users provide input-output tables.
Oh, tables, is it? Not the figure.
Oh, no, yeah, this figure is just for illustration. So they would provide like something that you can readily put into.
Okay.
Yeah. Any other questions? Rahul, did you?
Yeah, I was just wondering about connection of this to Stoke, because in Stoke also we were enumerating assembly programs, so it was real code, and there are hundreds of x86 instructions. So again, you get like hundreds of functions, and the search, when it was run, it was working with some IO examples, right? It was first trying to generate a program which will match the IO examples. So yeah, I'm just thinking that just thinking ahead, like I'm curious to see how when you talk about generators, then maybe you can say a line about how generators connects to Stoke, because we didn't have any idea of generators when we did Stoke.
I see. Yeah, so let me cover what I have on generators and things like that. I'll point up again. Yeah, makes sense. All right, so I'll proceed. So as I mentioned previously, the approach that we took was enumerative synthesis along with generators. So at the high level, given an input-output example, we have a program candidate generator that generates and checks programs against the spec one by one and just returns a solution when a program does pass the check, which is essentially the input-output example, right? So the main question here is how we generate program candidates. The programs we're aiming to generate are again straight line programs, which are essentially just sequences of function calls. So examples include this, like where here there's just a single function call, but you can also have chaining of a function calls by using intermediate output variables. And again, just to reiterate the point, it's important to generate valid candidates, something that do not error out. So for this, we need to capture the various constraints that I alluded to when it comes to pandas. And then this is where the generator idea came in, because we retain domain knowledge in the generator. So what does a generator actually look like? So this is kind of the a snippet or just a portion of the generator that we had within AutoPandas, and let me walk you through it. So the generator essentially is just a Python function that takes in the input-output example. And the first line within the generator is this call to sequence, which is an operator that is provided by us within AutoPandas. And what the operator does is that it takes a list of elements and outputs any sequence of elements from that list. So for example, if the input was pivot, melt, and drop, the output would the output can be pivot, melt followed by pivot, and or drop, pivot, and melt, and so on. So essentially, as you may have guessed, all these pivot, melt, drop are functions in pandas. So this first call to sequence would return a sequence of function calls to use within our program. Once we have the sequence, for each function in the sequence, we would decide the arguments one by one on a per function basis. So if the function selected is pivot, we pick the arguments for pivot. If it's drop, we do that, and so on. For picking the arguments themselves, we have we can use other operators such as select, which is again provided by us. Sorry, I think my slides, yeah. So we express the space of possible arguments using operators. So here the select function or the select operator takes in a list of elements and just outputs any element in this, just exactly what the name suggests. So if the input data frame was the one over here and the input to select is df.columns, right? So it's the list of columns. So you have date, category, and expense. So it can output category, it can output expense, it can output date, and so on. Right, so what is the highlight? What strikes you through this generator, right? So the first highlight that I want to show is that we are capturing constraints using arbitrary Python code. Every line of code within this generator is just regular Python, right? For example, we are using set differences to constrain the set of columns provided to select in this case. In this case, we're using if-else expressions to maintain that label and access constraint that I alluded to earlier, right? And the second highlight is that we are using the API directly, like df.columns. This is actually Pandas API. Because we're sticking to regular Pandas, we can do this sort of thing. This is unlike what you may have in, say, DSLs or grammars, where you're writing it in like more formal language, so you don't have access to the actual runtime or the API you're trying to synthesize code for. And the third highlight, the most important one, is that we're delegating this non-determinism or the space of choices to simple operators like sequence, select, subset, etc. And this is how it is connected to generators from the testing community. Quick check generators for creating random testing inputs. They pioneered this way of producing inputs, and we are trying to use that for the purpose of synthesis. It's also fair to see this as an analogous to sketch, because these operators they can be seen as wholes, where we're constraining the set of values that can happen, but that set of values is very dynamic based on the input output example. So that's where the difference comes in. But the kind of key point here is that since we're writing it within regular Python, it should be, if you have API expertise, it should be easy to write these generators for an API like this, because you just have to leave all the non-determinism to the operators. So for synthesis, you need to be able to control non-determinism, right? Because
so question here, Rohan.
Yeah.
Even though it is feasible, but if pandas has like hundreds of functions, it still becomes real tedious work.
It is tedious work. So that's why I said it's maybe straightforward, but not to say that it's not cumbersome. Yeah. So for synthesis, sorry. Yeah.
I'm also, since it is tedious work, I'm thinking that if someone makes an error in writing these generators, right? How hard it is like to debug the errors which will come about in doing this tedious work?
Good question. For this work, we just relied on it being able to solve simple synthesis problems to which we know there are solutions. So if it's not able to produce programs to solve that, and we create these problems for every individual function. So just like it's covering the space that we want. Otherwise, yeah, it's a good question.
As in, you would have faced this debugging experience.
Yeah,
right?
so that's what I did. I just like had like very small tests to kind of see if we are kind of reaching every possible program in this space by having these corner cases and testing for them. But apart from that, I don't know of a more kind of principled approach to that.
Did it take days to debug or weeks?
Oh yeah. I think the whole exercise was a week, like 2 to 3 days, just having this mad rush of writing these generator portions for all the functions, and then just sitting down and making sure that it's covering the space that we need. Yeah.
No, thanks.
So this, I have a question. This select is a choice operator, is it? It non-deterministically selects from the space?
Yes.
But
so
that also means, okay, I think you have this controlled non-determinism, right? Okay.
Yes.
Otherwise, search space becomes.
It is just random. Yeah.
Right,
It can just output any random program.
Right. Okay.
So thanks for the segue, Ravindra. That is exactly what I wanted to say. So for synthesis, you need to be able to control the order in which you're returning programs. So you need to be able to control the non-determinism. And the key idea here is that let's say for the sequence operator, you want to pick the sequences in decreasing order of likelihood or probability conditioned on the IO example. So based on what is going on in the end product example, you should be able to pick smartly what the most likely sequence of functions is, right? So you're trying to obtain the distribution condition of the IO example. Similarly, for the other operators, when it comes to select within the pivot function, you want to pick elements in the decreasing order of likelihood or probability, again, conditioning on the IO example, and so on. And you want to be able to do this for all the operators. So if all the operators are making smart decisions by conditioning on the IO example, you can smartly control the non-determinism and the order of programs that is being returned. So for all of these operators, the controller, so to speak, would be this probability distribution based on the IO example. And how to obtain this distribution, that's where the neural models come in. specifically graph neural networks, as I'll get into shortly. So how do the neural models work here? So let's look at an example. Suppose this is the input-output example, right? The input and output tables. And we're looking at the sequence function. So the model for sequence is supposed to give out a probability distribution over all the possible sequences, pivot, drop, and so on, conditioned on the example. So the first question is, how do you encode this? So,
Hi, this is
yeah.
Ravindra again. Sorry.
Yeah.
I have one orthogonal question here, which
Sure.
see, you have this label, column labels as date category and expenses. And in the output, you have lunch and social. I mean, how do you, so these queries, how do you pick up these labels? How do you match them? Which label should go where? For example, the date in the output, it is coming from date, but you don't have any label. How do you match those label?
Right. So I
The
think
column labels.
this encoding portion may answer your question. So
Okay.
let's see if it does. So the idea, so that also comes up when we want to encode the input-output example, right? So the model also needs to understand that. And the way we go about is that the first insight was that it's the relationships between the values that matter, not the values themselves. So even if I replace the value lunch with just say a string, but I recorded the information that they're equal, that value appears exactly the same in the input as well as the output. So I just mark them as equal. That is still retaining the information I need in order to be able to say come up with the transformation. And this relationship, because we can treat these cells as nodes and we can treat this relationship as edges, and therefore we can encode the whole thing as a graph. So the way we encode this is that we just represent all the values like columns, cells, and index labels as nodes, and we only retain the types. We throw away the values. By types, I mean integer, string, float, etc. And we use equality to capture the data movement. So we just compare the values. If they match exactly, we establish an equality edge. That's what we assume. Sorry, I think there's a typo here. Instead of string, there should be float. So just keep that in mind. Sorry about that. But in this case, since all the values in the expense columns are appearing as this 2D grid over here, we have equality edges that are shown here. Similarly, for the category column and the lunch social column, because the values match exactly, we just establish edges. Then there. Similarly, for the date column, we just match the values exactly and capture that relationship. So overall, the encoding, and we also use structural edges. So in the 2D structure of the table, there are rows, there are columns. So we just retain that information as edges. So overall, the graph looks like this, and it captures these relationships. And the model, then we just use an off-the-shelf graph neural network with an RNN head, because this is sequence, we need to output a sequence of functions. And it takes we train this model to take this graph in and have a distribution over the sequences. Coming back to your question, Ravindra, does this make sense?
Yes, yeah.
Awesome. The next big question is, how do we actually train the model for this, right? So how do we get training data for these sorts of things, for this sort of modeling? There's no readily available corpus of data that we can just train all of these models for each of the operators with, right? So we need input, output, and program tuples so we can train each of the operators individually in their very specific task of picking something from a given list of elements. And the kind of big idea here is that we simply reuse the generator, because if we have random semantics for each operator, so instead of smartly controlling non-determinism, we just say, just pick anything you want. And if you provide it a random input data frame, because of the generator having all of the constraints in the pandas library, it is guaranteed to return correct solution, valid programs. So if you have all the operators making random choices, you get a random program out. And you can simply execute the program on the random input to get a random output. So it's very easy to freely generate training data for the models. So yes,
Rohan, can you go back to that to this graph neural network? What exactly does it give you as output?
Sure. So that's so for the sequence operator, right? All the possible state essentially gives you a probability distribution over all the possible sequences. Because there's an RNN head on top.
Okay, so these are sequences that will give input-output behavior that matches this graph, is it?
So this is just one piece of the puzzle. This simply decides the functions I want to use in my program, and then you have the other operators for deciding the arguments for those functions.
Right. No, I mean, what would the, for example, if you want to train this, what would be a input-output example?
Oh, right. So that's where this random generation comes in, right? So if we have a random input and all of the operators are making random choices, you can track those choices and you can get the end program that is coming out as a result of all these choices. And once you execute the program, you'll get the output, right? So once you have the random input and output, and you have also tracked the choices made by each of the operators, you get these kind of training data for each individual operator. If that makes sense.
Okay, so the only relationship you're keeping in the graph is that is the equality of entries, is it?
Yes.
Okay.
I'll quickly go through the evaluation. Evaluation we collected a small set of real-world Stack Overflow benchmarks, which had various depths or the number of functions required to solve that particular task, ranging from 1 to 3. And we found that we could solve about 17 or 26, 65%. Encouraging, not the best, but still quite good. And the kind of good thing was that we could find programs that contained 3 function sequences. And the good thing about this is that 90% of accepted answers on Stack Overflow we checked, they could be solved by using programs that contained up to 3 functions. So if you're able to solve these sorts of tasks, you're already covering a lot of functionality. And most of the solutions that were found, or the cases that we solved, the solutions were found in the top 10 function sequences. So the models were doing their job. They were effective. They were very effective in biasing the search space towards the right solution space. So we did have a prototype, and I'll show you a video of the website that we made for AutoPandas. But the main kind of contribution or idea behind this work was the introduction of these generators as this unified abstraction of the space as well as the algorithm, because the models are very much included within the generators in form of those operators. And because these generators are written in regular code, it overcomes the limitations of canvas and DSLs when it comes to modeling very complex constraints, etc. And it also indirectly gives you a nice way of combining the decisions of many small models. Every single operator is supposed to do a small task, but you have this regular code that is combining the decisions of all of the small models into this one big program. So with AutoPandas, we tackled pandas, we introduced generators, we used graph neural networks because we are modeling input-output examples as graphs, and we saw encouraging results on Stack Overflow benchmarks. And before I open this up to questions, I just want to show you a demo of the website that we had for AutoPandas. This is a prototype website we created for AutoPandas. On the left here is a mechanism to provide input-output examples. One can use code as shown here to initialize the pandas data frame and click preview to see the result. One can also just modify the data frame directly if that's what they prefer. And once the input-output example has been finalized, one can click Synthesize to ask AutoPandas to get the results. And if we like a particular result, we can simply copy the code and paste it into our own workflow. Yeah, so before I move on to the next part, any questions?
Yeah, Rohan, it's Alvin.
Yeah, hi, Alvin.
So that select operator, it's essentially picking one using a probability distribution. That is, but it doesn't solve any inferences or like constraints with the with an operator that precedes it.
Yeah, it doesn't kind of interact with all the other operators, if that's what you're asking. Yeah.
Okay.
Yeah, it just has a very specific role, right? Okay, these are the list of elements, just pick the best one according to the input-output example.
But the smartness comes from the distribution itself, how you...
Yes, yes. Well, what you're suggesting could be done, like you could improve on this by having more complicated models work together for each of the operators, but we just went with the simplest thing.
Okay.
Also, before I move on, Rahul, you had wanted to...
Yeah, I was going to ask the favorite question, which is asked for all programming by example systems, right? That don't see instances of overfitting, that like the code which comes out matches the input-output example, but of course is not the intended code.
Yeah, that's definitely the case. Like even in the video and in the right section, there were multiple solutions, right? But it's hard to know just by looking at them, like how they really differ. We did have one idea that we tried exploring, but didn't really. We kind of abandoned it in the middle. But the idea was that if we could generate distinguishing inputs for multiple solutions, just to show to the user how two solutions differ, maybe that can kind of aid their comprehension into picking the right one. But just by itself, just having one input-output example, the overfitting problem is not going to go away.
Well, for a distinguishing input, you will need like a symbolic execution engine for Python pandas, right? And that's not going to...
Yeah. You could also just use the random input generation technique and just hope that it would, come up with something within some reasonable amount of time. Yeah.
Hope.
But I think like my next paper also kind of tries to tackle the overfitting problem to some extent, and hopefully that's interesting too.
Okay.
Yeah.
So Rohan, I had a question about I think there was some earlier work, I forget the name of it now, which they use, similar problem. They want to kind of compose, functional, they want to get a functional program like using map and filter for some input-output examples. And I think they also do something similar. They have some kind of a probability distribution on the, how likely is a particular function like map or filter to be used.
Right.
Deep
coder. Right. Yeah.
So I guess the only difference here is that you are maybe using this graph neural network to maybe
the graph neural network, and also like multiple small models that are being composed together with the operators. Like within deep coder, kind of the decision point was very early on, like, okay, what are the functions in the DSL we want to use? And then you had all these like enumerative search, or I forget what the kind of other backends they combined with were. But the kind of the neural part was really at the top. And then there was only a single one. But with this generator thing, like the many small models that are combining together using the generator. So that's kind of the difference.
Okay.
All right, so let's move on. And to kind of introduce the next piece of work, I want to kind of give a bit of experience that we had while presenting auto pandas to some some of our industry sponsors there at Berkeley. And kind of the highlight of that discussion was like whether input-output examples are really the right modality when it comes to synthesis for this particular domain. So more from the perspective of productivity, like would you want to use something like this? Would you be willing to provide input-output examples for every task that you have a problem with in a natural setting? It does come up on Stack Overflow, but does that mean that you would want to do it on a daily basis, or something that you would incorporate in your daily workflow? And kind of the overwhelming majority of responses were that you probably want to improve on this in some way. And kind of the two major reasons that were highlighted of why input-output examples may not be the ideal specification modality for this problem are information loss and tediousness. So let me elaborate on that. So consider this following input-output example, right? To synthesize a program for this example, the synthesis engine must determine how 102.5 in the output is being computed, either via reasoning or by trial and error. 102.5 here is, in fact, the average of the 4 cells in the low and high columns, 50, 70, 100, and 190 over here in the pants rows. But this information is already known to the user, otherwise they wouldn't be unable to create the example in the first place. So the result of this is that readily available information is lost. From an engine standpoint, this loss can be critical. It can lead to a loss in performance and an increased chance of overfitting. It may be able to come up with a solution that arrives at the value 102.5 in a different fashion than the one that was intended by the user. And the other problem is that imagine if the input table had many more rows now, which is highly unlikely for a table containing, say, inventory details like this one. And like having a table with, say, 50 or 100 rows is very common when it comes to data sets, or even the majority of tables would be even larger than that. So in this case, specifying the complete output would defeat the purpose of synthesis entirely. Providing the example can be tedious. The only other option is for the user to create a small artificial example and then adapt the solution. You can't just provide the full output here. So this can get tedious, and it can hamper the productivity of the users and the overall usability of the tool, because if you stick to input-output examples as the modality. So this was the problem that we tried to tackle with our follow-up work, the system called Gauss. And before I dive into what it does, let's see a video of the capabilities of Gauss, or kind of the new modality that we introduced with Gauss. So let's see. Here's how we can use Gauss to synthesize transformations. Gauss is integrated within Jupyter Notebook, and it provides a UI to incrementally construct the output from the input. Let's compute the average of the 4 cells using the inbuilt operations provided by Gauss. In this case, we select mean because we want to average the values of the 4 cells. Once we click mean, the result is copied into the clipboard, and we can paste it into a cell in the output using Control-V. The cool thing about Gauss is that we do not have to complete the output. It accepts partial outputs. So in this case, we can go ahead and already click synthesize. Instantly, Gauss figures out the solution and provides the complete output along with the code. Moreover, we can click on the cells in the output to verify that they're computed correctly. In this case, we can also verify that 95 is indeed computed as the mean of 80 and 110, which was the intention. So just to recap, as you saw in the video, Gauss introduces a UI which captures interaction, where users incrementally construct the output using inbuilt operations that are provided by Gauss. It's worth to note that all these operations are rather primitive. You can apply them to any selection of cells. So they do not necessarily correspond to the exact operations offered by the API. They just very primitive relations between the input output. And the big thing about Gus is that it can accept now partial outputs. You don't have to provide the complete output or spend time completing the output. And the way Gauss captures the interaction is as a graph. So in this case, 102.5 was computed as the mean of these 4 values in the input, right? So again, like similar to how what we did in AutoPandas, we represent this interaction as a graph. So you can see these special mean edges that are going to this intermediate edge that then has an equality edge with the output cell. So this graph overall captures the fact that, okay, this one cell in the output is actually the mean of these 4 cells in the output. So you're retaining that information. You're not losing it as would be the case in display input output examples. So in this way, Gauss preserves readily available information. And as you saw in the video, that you can already click synthesize. It accepts partial outputs and it synthesizes a program in R or Pandas. And you can have the full output of the program. So not just 102.5 now, the output contains the values for all the other cells as well. And kind of the message here is that, or the hypothesis is that since we are using partial outputs, it invariably means less burden on the end users because you do not have to spend time constructing the whole output. So what is the new synthesis specification that we're introducing, or the modality? So along with the input table and the partial output, you're also recording this user interaction or the user intent very explicitly. So in this case, it was 102.5 is the mean of these 4 values in the input. And a program satisfies the spec if its output contains that partial outputs. In this case, it contains that value 102.5, which is specified as part of the partial output. And its behavior must be consistent with the user intent. So this is like this extra check that we're adding on beyond the input output example. But how do you actually operationalize this consistency? This is where the graphs come in again. The constraint that we are imposing is that the user intent graph, as recorded via interaction, must be a subgraph of the graph abstraction of program P. So what is a graph abstraction of program P? The graph abstraction of P essentially captures the behavior on the given input as a graph. So here you have this full program containing these two functions, right? So it essentially captures, the relationship between all the cells or columns in the input to all the cells and columns in the output, right? So it contains all the edges that define the relationship between the input and output. And the subgraph check essentially, intuitively means that you're doing, or you have all the relationships as specified by the user in the overall relationship graph that you obtain from the program. So in case you don't believe me here, the G user is, this part of the subgraph, and that is below, which is essentially the graph abstraction of P. Any questions till this point? Awesome. So this consistency check, as I said, it enforces a stronger match with the user's intent, right? But the big question here is, how do you obtain this graph abstraction of a program? So at a very high level, we just reuse the generators we had before. So in AutoPandas. So instead of just constructing the program, since we are working with regular code, we can also kind of influence the generation. We can also create the graph as we construct the program. So we modify the generators for the individual functions to return graphs along with the function calls. And the graph, so for each function call, we would have a graph, and then we actually compose it together to produce the final graph abstraction of program P. So let me show you an example for this. So for example, in the program, we had 2 function calls, right? So for The first function call here is gather. So we modify the kind of generator portion for gather to also produce this particular graph, just to say just the input and output of this one function call. So we get the graph as shown here. And then the second function call, we take the input, which is the output of the previous function call. And then we create the graph just for this function call, which is represented over here. And then we combine the individual graphs to capture the overall effect between the initial input and the final output of the program containing both the function calls. And the way we do this is we propagate the relationships using equality edges. So if the first if the first cell is equal to this cell, which is again in turn equal to this particular cell, then we can establish an overall equality relationship between the first and the last cell. And similarly, if you have a mean edge in between, and if the first cell is equal to the second cell, you can propagate the mean relationship back to the first cell. So this is how you can fuse the two graphs and have an overall relationship between the input and the output. And this is how you obtain the graph abstraction of a program. Any questions so far? Awesome. I do want to pause here and just ask, like, well, what is the constraint on the time? Do I need to close in 5 minutes?
Yeah, I think you have time. There's another 5-10 minutes maybe.
All right. In that case, I would like to move on to the kind of next tool that I have. I don't think I would have time to go through all the kind of technical details of cows.
Okay, so Rohan, I had one question.
Yeah.
It's a vague question. So is it,
Yeah.
I mean, it looks like have you explored, a logical way of specifying the input instead of this input output examples? For example, saying that the cell is the mean of these 4 cells. One could, do that in a logical way, like similar to what they do in, is it in Cygus or one of these? I mean, the specification is a logical constraint over the inputs and outputs.
Again, so like in this particular example, right, like taking the average of the things, it's very much dependent on the so I'm not sure actually how to kind of generalize that for every input and output, because that would essentially mean that you're capturing the semantics of the functions and themselves for every possible input and output, and also able to compose them.
Yeah, maybe you're capturing the transformation, or maybe partially.
Yeah.
But how to do it still has to be synthesized.
Yeah. Because again, this graph just captures relationships. It still does not tell you how to actually combine the semantics of operations or functions to achieve this particular effect. So the kind of the specification we're going with here simply has more information. It's not too vastly different in terms of the power as compared to input output example. All right. So again, since we're short on time, I'm just going to can go through just the eval just a bit. So again, we want to look at synthesis performance, right? So we compared against 3 prior state-of-the-art systems where which were only provided input-output examples, not the extra information that was coming from interaction. And the hope was that we would gain in terms of efficiency and the number of programs that we have to search because we have this extra information. So we found that on most of the benchmarks, we were close to 7 to 8 times faster than all of these other systems because we had this additional graph information coming from interaction. And this essentially stemmed from the fact that we were exploring far fewer programs in the enumerative search section as compared to these other systems which just had to work within product examples. Orders of magnitude fewer programs because of this extra use of graphs as the modality. And we also found that if we use this partial outputs, right, we wanted to quantify the benefit of using these partial outputs as compared to, say, just providing the full input output example. And we found that you could still have, obtain the right solution, no overfitting is like the correct ground truth for a synthesis problem, even by specifying, a partial output that is 33 times smaller than the original output on average. So this kind of somewhat gives you an idea of the quantification of the reduction in burden when it comes to the end user. And we even had an informal study where we had participants use Gauss as compared to, say, some other tool, like using Google to solve a problem using a particular API. And most of them were able to solve. So one of them was able to solve all the tasks, and the others all 8 out of 10. But the overwhelming consensus, or the consensus was that Gauss was much more preferable as compared to using these search engines or coming up with the solution in a different way. So we had some encouraging results in terms of productivity, or the benefit of using these tools in practice. So and in the need to kind of bounce around a bit because we're short on time. But in the third piece of work, we wanted to tackle visualizations, data visualization, synthesizing code for that. But the kind of the key difference about the key challenge in this space is that it's hard to provide checkable specifications, because how do you check a generated program or visualization against the user's intent? Because the user cannot provide the output visualization, as was the case for input output examples for data transformation. Because if you provide the output viz, you're defeating the purpose, right, of creating the visualization in the first place. And sometimes users often do not know what they want. You want to explore all possible visualizations and pick something that they like. So you do not have a checkable specification beforehand. And they might have a concept in mind. They say they want to visualize correlations, but not the exact kind of visualization. So it's more higher level. There have been prior works like exploring partial visualization outputs, but again, they're very limited in scope and the types of visualizations that can be produced. And you have to there's no scope for error, essentially. And again, how do you define the search space? Because if we kind of try to use the DSL grammar or generator approach, it may be unwise, because creating visualization often involves data processing and shaping operations. The search space is already larger because you're tacking on to the space that was used for autopandas. And now you also need to account for variations like color variations, labeling, legend placement, so the stylistic variations. So the space is just huge. And if you try to constrain it in any reasonable way, it might be unwise. You may be leaving out visualizations or plots that users actually want. And they are even more unstructured than pandas, so it's a difficult choice. So with Smith, our third paper, what we did was, because we had to deal with weak specifications, we started accepting natural language descriptions, where users can view and select amongst multiple return visualizations. But the kind of big thing here was that we introduced another search space option, crowdsourcing. So what we did was we mined visualization code from Kaggle and templatized it and created a database for use in synthesis. So now the search space was crowdsourced in the sense that whatever users have done on platforms such as Kaggle, all of that is fair game, and you can create visualizations using that. So the insight here is that let's just use what people have done in the past. So again, I don't think I did have a video prepared. So here's how we can use Vismit to create visualizations from natural language. For our first example, we load a voice call quality dataset as a pandas data frame as shown here. And suppose we want to analyze the distribution of call ratings in this column for every network operator individually. We call Vismith using the synthesize function here, and we pass in the data frame and the columns to visualize as shown here. Suppose we know the type of visualization we want, a normalized stack bar chart. So we can go ahead and put in the type of the plot in the text query. In a few seconds, Vismith comes up with a number of visualizations. We can zoom in on a visualization by selecting expand, and we can even look at the code if we wish to check if it's doing the right thing. If we particularly like a visualization, we can click select, and this will copy the code into a new cell for ready use. Let's look at another example. Suppose we have a data set of Netflix titles, and we want to visualize the distribution of the type of the shows. And for this, a pie chart sounds good. We can fire up Vismith just like before. We pass in the name of the column type. And for the search query, we can provide something like pie chart counts. And very soon, Vismith comes up with a few suggestions for the pie chart. Let's look at this one. This looks actually pretty good. It has all the axes labels, the values of the percentages in the distribution, as well as different colors. In this last example we have, suppose we want to visualize the missing values or the NANDs in the Titanic dataset in some way. It's not immediately clear what type of chart to use. We can let Vismith figure this out for us. Instead of providing a specific kind of visualization as the query, we can provide the concept that we want to visualize. In this case, we can simply put in missing values. And Vismith would come up with a number of ways of visualizing this information. Let's look at this one. In this case, it's visualized the missing values as a heat map. Every bar indicates the presence of a missing value in that column. And it's very clear from this visualization that there are 3 columns with missing values. Another way to look at the same thing is this one, where Vismith has come up with a visualization that is a bar chart of the counts of the missing values in the 3 columns that actually have them. So within Vismith, as I mentioned, there are 2 key things: natural language and crowdsourcing, right? So there's this offline phase where we mine Kaggle to create a database of mine visualization functions, such as this one. And during the online phase, what we get from the user is the data to visualize, the columns to visualize, and a text query describing the visualization. And then we use the database. We match the function metadata against the queries and then give a ranked list of visualizations. So this is the way we overcame the challenges that came with the domain of synthesis for visualizations using this crowdsourcing idea. Again, I do want to do a quick check with regards to time, if I can cover another section or if I should close here.
Yeah, I think maybe we should wind up now because over an hour.
Yeah, sounds good.
So, yeah, you want to conclude, or maybe we can have questions of.
It's probably good to open this up to questions because that's the most interesting part. But just first, thank you to all my collaborators from Berkeley, Fujitsu, for all these projects. I'm happy to take questions at this point.
So, are there any questions?
How close are the programs generated to a handwritten one in the first?
The AutoPandas work?
Yeah, AutoPandas.
Great question. I don't think we have a sense of that. It's hard to say because it can generate every valid program in this space. So there are chances it may use an in-argument combination or something that is a bit more unnatural with the way people use things. But you could imagine, another layer on top of it, which if there are multiple solutions, it could bias based on the naturalness or something to kind of increase the quality of the code return on that aspect.
The thought was, is it easy to understand?
Yeah, I mean, it does include all the functions and the arguments. We do not have an auxiliary documentation book that explains what is going on. But maybe that could be something that could be added.
I guess the question is how does the user know whether, which of these programs to pick? I mean, which is the one that they want. So do they, for example, do they generate more data, data and have a whole back kind of set and check?
Yeah, so since we only have one in-prop example, it's hard to differentiate apart from looking at the code. But that's where I had made this point previously, that we explored this idea of distinguishing inputs, or finding inputs which kind of showcase the differences between the programs. But yeah, we didn't really come up with solutions for that.
Okay, so in the visualization work, these Kaggle programs that you have they come with some comments and say what it's doing, and then that's the data that you match with.
Yes, exactly.
With the search query. Okay.
Yes.
Okay, that's interesting. Any more questions? Okay, right, Rohan. So yeah, thanks a lot for a great talk. Very interesting, and I think many maybe new to many of us in this community, but it was nice give an idea of the kind of techniques that are used here. Right. Okay, so thanks a lot.
Thank you very much for having me. Thank you.
Thanks, Ron. So Madhukar will stop the recording.